Welcome back to Integral Calculus. This is my first lesson on volume of solids. Volume by cross-sections. If S is a solid that lies in the interval AB along the x-axis and has a continuous cross-sectional area defined by A of x, its volume is given by this: the integral of A of x dx from A to B. How this came to be is comparable to how we defined the definite integral as the area of a plane region bounded by a function. So we begin by slicing these solids into sections, and each of these sections forms a prism. And each of these prism has a volume, and the volume is given by this. It is equal to the area of the base times the height, which in this case we call delta x. So the volume of that solid, or an estimate of the volume of that solid, is going to be this. It is equal to the sum of the areas of each of those sections times delta x. The true volume of the solid is going to be this: the limit of the sum of all those volumes as n approaches infinity. And if the limit exists, that is what we call the volume of this solid, which is computed in this way. It is equal to the integral of A of x dx from A to B. Using definite integral, verify that a rectangular prism with a cross-sectional area of 4 square units and length of 5 has a volume of 20 cubic units. So this is a prism. And we know how to compute for the volume of a prism. We multiply the area of the base by the height of the solid. In this case, it's going to be 20 cubic units. The volume is equal to 20 cubic units. Now let us verify that using definite integral. So the volume of this solid is equal to the integral of the area. In this case, it's constant. It's 4. It's 4 dx from 0 to 5. And it is equal to 4 times 5 is 20 minus 0. It's 20 cubic units. Solids of revolution, disk method. Revolution around the x-axis. So what is a solid of revolution? In this case, we are revolving a plane region around the x-axis. So a solid of revolution is formed when you revolve a plane region that is above or below the fixed line. In this case, our fixed line is the horizontal axis, the x-axis. Okay? And how shall we get the volume of that solid of revolution? So if you revolve that plane region around the horizontal axis, it will trace a solid whose cross sections are disks. Okay, disks with a radius that is equal to f of x sub I. Okay, and the area of each of those disks is equal to this. It's pi times the square of the radius. So it's going to be pi times the square of f of x sub I. Okay, so where is f of x sub I here? The length of that vertical line, the radius of a disk, will give you f of x sub I. Okay? And the area of that disk is equal to pi times the square of the radius, which is equal to the square of f of x sub I. Now, let us be clear with terminologies here. Strictly speaking, a circle has no area, okay? Because a circle is a set of points, and points have no dimensions. So when we talk about area of a circle, we are referring to the area of that region that is bounded by the circle. And in math terminology, we call it the disk. So strictly speaking, the disk has an area, but the circle does not have. When we say area of a circle, we are referring to the disk. The plane region bounded by the circle. And so imagine this section to have some thickness about it. So it's going to seem like a very thin cylinder. And you know how to get the volume of a cylinder. It's the area of the base times the height. In this case, it's delta x. And so again, going back to how we are doing it, if we want to get the true volume of this solid, we will do this. Okay? A solid of revolution, and we can compute for the volume of that solid of revolution in this way. It is equal to pi times the integral of the square of f of x dx from a to b. So I hope that you are not kind of intimidated by this, because the foundational ideas here has something to do with circles, area of circles, and the volume of a cylinder. So when you look at this, that is just your formula to get the volume of a cylinder. Verify that the plane region bounded by f of x is equal to 2 in the interval 0 to 6 when revolved around the x-axis has a volume of 24 times pi cubic units. So when we revolve this plane region, the region above the x-axis, around the x-axis, you will form a cylinder. And using what we know about cylinders, the volume of a cylinder is equal to the area of the base times the height of the cylinder. And the volume of that solid is going to be 24 times pi cubic units. Okay, so that is what we expect to get when we use definite integral to get the volume of the solid of revolution. So let us set up the definite integral. V is equal to pi times the integral of f of x squared, okay, dx from 0 to 6. So it's going to be 24 pi cubic units. Okay? How about this? Find the volume of the solid in the closed interval 0 to 2 formed when the plane region bounded above by f of x is equal to x squared and below by the x-axis is revolved around the x-axis. Okay? So you will form a solid that looks this way. It's like the horn of a trumpet. Let us set up the integral. So the volume is given by this. It is equal to pi times the integral of your function squared. Okay? So it's going to be x squared dx from 0 to 2. The integral of x to the 4th is going to be x to the 5th over 5, okay? And then evaluated from 0 to 2. And so you know how to do this. So it's going to be equal to, okay, 2 to the 5th pi over 5 minus 0. And that is equal to 32 pi over 5 cubic units.